Welcome to the deep dive. You know how this works. We take all the complex research, the scattered notes, and we distill it all down into the context you need. And today we are focusing on a visitor from outside our solar system that is, well, it's really rewriting the rule book on galactic travelers.
We are jumping right into 3I Atlas, and I think you could argue this is the most important object to fly through our system in a generation.
Absolutely. It's only the third confirmed interstellar object we've ever seen. First, there was 1I Oumuamua, then 2I Borisov.
And just the fact that we've now seen 3 of these things is a huge scientific achievement in itself.
It really is. And you have to remember, each one of these is basically a physical sample. It's a piece of another star system, light years away, delivered right to our doorstep. So our mission for this deep dive is to unpack all that data we're getting from the sources, the observations from the James Webb Space Telescope, the reports from our spacecraft out at Mars, and really get to why 3I Atlas is causing such a scientific stir. It really boils down to 3 things.
Yeah.
It's absolutely shocking size, it's incredible age, and it's genuinely bizarre chemistry.
So for anyone just catching up, 3I Atlas, its official name, the one on the books, is C2025 N1 Atlas. It's an interstellar comet. We first confirmed it back in July of 2025.
And it's on what they call a hyperbolic trajectory.
Exactly. Which, is just a way of saying it's moving way too fast to get captured by the sun's gravity. It's just passing through. Our solar system is basically a gravitational slingshot for it on its way back out into the galaxy.
Okay, and before we get into the really wild stuff, let's just do the quick safety check for everyone. This thing is not coming anywhere near us.
Not even close. It's extremely distant. It already made its closest pass by the sun. That's called perihelion back at the end of October.
And even then, it was way out there, inside Mars's orbit, but still well outside ours, about 1.35 AU.
Right. And just as a reminder, an AU is an astronomical unit. It's the distance from the Earth to the sun, so about 150 million kilometers. So 1.35 AU is already pretty far. But its closest approach to us, to Earth, is happening in December, and that's even further out. It'll be about 1.8 AU.
That's something like 269 million kilometers.
Yeah.
It's purely an object for our telescopes. It poses zero threat.
Zero. It's just giving us this incredible chance to look at a piece of the cosmos that formed billions of years ago.
Billions of years ago. I think that's the perfect place to start because when you dive into the age estimates, the timeline is it's staggering. This isn't just a comet from another system, it's a time capsule.
That's it, exactly. What's so revolutionary about Atlas is its potential age. Based on its orbit and its chemical makeup, the analysis suggests it might actually be older than our entire solar system.
Older than our solar system? Wait, our system is what, about 4.6 billion years old?
That's right. So we could be talking about an object that's 7, maybe even 8 billion years old.
So it formed before the sun was even a thing.
That's the implication. The thinking is that it probably came from the Milky Way's ancient thick disk.
The thick disk. What exactly is that?
You can think of it as the galaxy's senior citizen community. It's the older, more chemically basic population of stars and gas that formed way back in the galaxy's early history. So this object has been wandering through space for eons. That makes it a direct probe of the kind of material that existed long before the cloud that formed our own star ever came together.
That really puts it in perspective. It's been traveling for longer than the Earth has existed. But here's the real aha moment from the sources, the detail that just sets Atlas so far apart from the others. The scale.
Oh, yeah. The mass estimate that came out of the James Webb data is what really sent a shockwave through the community. We are looking at a minimum diameter of 5 kilometers, and the mass that goes along with that is somewhere around 33 billion tons.
5 kilometers. Hold on. Oumuamua was what, a few hundred meters long? And Borisov was maybe a kilometer across, tops? This is a literal mountain flying through space.
It's an entirely different class of object. I mean, it is orders of magnitude more massive than Oumuamua and Borisov put together. It's not even in the same ballpark.
And that's surprising, right? Because we shouldn't be seeing things this big wandering around.
It's fundamentally surprising, yeah. The theory was always that interstellar space would be filled with little bits of debris. Statistically, objects this large should be incredibly rare. They should have been captured by a star system or destroyed billions of years ago. The fact that we saw one tells us something really dramatic about how many large comets are just floating out there.
And that size, that mass, it tells us a lot about its durability, too. It has a direct effect on how it moves.
It does.
We know from the sources that as it got close to the sun, it started heating up and losing mass like crazy, something like 150 kilograms a second.
which is a huge amount of outgassing. And normally that acts like a little rocket engine. It gives comets a noticeable push, a little non-gravitational acceleration.
Right. It should knock them off course a bit.
Exactly. And while they did detect that it was moving off its gravitational path by maybe 94 kilometers per day squared when it was at its closest to the sun, the effect was tiny.
So even with 150 kilograms of its own mass blasting off every single second, it barely budged.
Precisely. That is the perfect demonstration of its inertia. This huge 5-kilometer nucleus just resisted being pushed around. It had so much bulk that all that constant jetting only caused this tiny, tiny deviation. That minimal deflection is physical proof of just how massive this thing is.
That really gives you a sense of the scale. Okay, let's connect that scale to its chemistry, because the sources suggest that its age and mass help preserve some truly extraordinary materials inside. Why is its chemistry so different from a regular comet from our own solar system?
Well, you have to think about that 7 billion year journey first. All that time spent in deep space actually prepared its surface.
Oh, so
Over all those eons, it was constantly being bombarded by high-energy cosmic rays. And that radiation cooked the outer crust, creating this highly irradiated layer that might be, 10 or 20 meters deep.
it basically built up its own protective shield over billions of years.
A cosmic shield, yeah. And that process, that bombardment, it converted simpler molecules like carbon monoxide or CO into more stable ices like carbon dioxide, CUS. And that shield protected all the pristine, volatile stuff deep inside. So when it finally got close to our sun and started to heat up, what came streaming out was highly unusual.
And the big signature was that it was really rich in use.
Right. Extremely rich. The coma, that's the gassy atmosphere around the nucleus, is just loaded with carbon dioxide. It's far more abundant than water vapor.
Which is the total opposite of our comet.
The complete opposite. Most comets that formed in our solar system are dominated by water ice. This extreme CO to water ratio tells us that 3I Atlas must have formed in a much, much colder and chemically different place than the outer edges of our own system.
What other weird things did we see in that gas?
Well, besides all the COs, we also picked up signs of gases like cyanide and, pretty surprisingly, nickel vapor. This is all what you'd expect from very old, very volatile ices finally getting heated up. And it was so dramatic that you could see it visually. The comet actually changed color in our telescopes, shifting from a kind of reddish color to this very distinct green as all these exotic gases lit up.
That green glow that usually comes from a molecule called C, right? Simple carbon chain molecule. But the sources say that C seems to be missing from the data.
And that's a really strange contradiction.
Yeah, if it's glowing green, why aren't we seeing the usual culprit?
That's one of the big chemical puzzles we're still trying to solve. Its composition is telling us a story we've just never read before. But speaking of things we've never read before, we had to talk about its optical properties because the observations revealed something completely new, this extreme negative polarization.
Okay, let's unpack that. It's a very technical term.
Okay.
What is polarization, and why is this object's behavior so extreme?
So, polarization is just about the alignment of light waves after they bounce off a surface. Think about polarized sunglasses. They block light that's scattered horizontally, which is what cuts down the glare from, say, a wet road.
Right.
Well, the light that bounces off every comet and asteroid we've ever studied behaves in a predictable way. It usually shows what we call positive polarization when you look at it from certain angles.
But 3I Atlas did the opposite.
Exactly. It shows an extreme negative polarization. This behavior is, and I'm not exaggerating, utterly unprecedented. It is the first object ever seen with these polarimetric characteristics.
So what does that even mean?
It suggests that the texture, or maybe the shape or the composition of the dust grains coming off this comet are fundamentally different from anything that formed inside our solar system. It basically breaks our standard model for how light should interact with cometary dust.
So it's not just the oldest and the biggest interstellar visitor we've seen. It also reflects light in a way that suggests its building blocks were formed under conditions we don't even understand yet. It's astonishing.
It is. It really just highlights how valuable these interstellar samples are.
Which brings us to the observations themselves. I mean, it's just a huge success story that we had spacecraft in the right place at the right time to even get this kind of detail.
This was a real triumph of orbital mechanics and also international cooperation. Because 3i Atlas passed relatively close to Mars in October 2025, we have this perfect viewing platform waiting for the Martian fleet.
And what kind of data did we get from NASA's MAVEN orbiter?
MAVEN, that's the Mars Atmosphere and Volatile Evolution Orbiter. It was absolutely crucial. We used it to look at the comet's huge hydrogen coma in ultraviolet light. This lets you map out how the volatile gases are spread out really far from the nucleus. It gives you compositional data you just can't get from Earth because our atmosphere blocks that kind of light.
And the European Space Agency's orbiter also played a big role, I remember.
A huge role, yes. ESA's ExoMars Trace Gas Orbiter, or TGO, got these incredibly detailed photos as the comet flew by. And what's really key is that those different viewing angles allowed scientists to massively refine the comet's trajectory.
How much better?
TGO's data improved the accuracy by a surprising tenfold. It hugely reduced the uncertainty of where 3i Atlas is going next. That's observational gold. It means we can track it precisely as it leaves.
And in those images, we saw some visual oddities, too, like something called an anti-tail. That just sounds like a contradiction.
It does, doesn't it? Normally, a comet's tail always points away from the sun, pushed by the solar wind. An anti-tail is a rare visual trick. It's an optical illusion, basically. It happens when heavier dust particles, which don't get pushed away as fast, kind of trail behind the comet in its orbit. And if you here on Earth are looking at it from just the right angle, that trail seems to point toward the sun. It's all about perspective.
A trick of the light.
Trick of the light, exactly. The comet also had multiple jets and tails coming off it. Very complex directional outgassing.
Okay, so finally, we have to touch on the conversation that seems to pop up every time we find one of these unique interstellar objects. The sources all mention the public stir.
Oh, absolutely. Whenever an object shows unusual behavior, like that minimal non-gravitational acceleration we talked about, it raises questions. And the astrophysicist Avi Loeb and his team publicly brought up the hypothesis again that maybe that acceleration could hint at, well, artificial control.
The same alien tech idea that came up with Oumuamua. And that, of course, grabbed all the headlines.
Of course it did. But it's really important for you, listening, to understand where the scientific consensus is. While that idea sparked a lot of discussion, the vast majority of researchers agree that all the data we have is perfectly consistent with normal comet physics. Given the incredible mass of 3i Atlas, that tiny little nudge it got is completely explained by complex natural outgassing. The consensus is that 3i Atlas is a natural, if extraordinary, comet.
So let's put it all together for the listener. 3i Atlas isn't just the third interstellar object we've seen. It's a 5-kilometer wide, chemically unique giant. A time capsule.
That's the core takeaway. It's a 7 or 8 billion-year-old traveler. It's showing scientists what an ice-rich body looks like after aging for eons in the vacuum of space. Its exotic chemistry, all that preserved cocos, its unique optical properties. It all provides this invaluable insight into what the galaxy was like in its ancient past. We're learning about the raw materials that existed before our sun even formed.
And that's the real relevance here for you. This isn't just some abstract fact about a distant rock. It's a direct sample from the birth of the galaxy itself. So that leaves us with this final thought. If the material of 3i Atlas really does predate our sun, what else might these unique ancient cosmic travelers, the ones still out there waiting for us to find them, tell us about the very first stellar nurseries in the Milky Way and the elemental building blocks of the very first planets?
The question for scientists, as this object vanishes back into the interstellar void, is this. How much of the original pristine chemistry of its home star system is still preserved deeper within its massive, protected core? And how will we design future missions to actually punch through that irradiated shell to sample the true original conditions of a 7-billion-year-old birthplace?
That is the ultimate mystery that only these ancient travelers can pose. Thank you for joining us on this deep dive into 3i Atlas, and we encourage you to keep looking up and stay curious.